Okay, ladies and gentlemen, welcome to the first edition of our videos of teaching during the walkouts. So today we're going to talk about the first part of section 5.2, which is about linear regressions. Now, some of you who had me last year, we talked a little about linear regressions. And the first thing you got to know in order to do linear regressions is linear equations, right? So what I was going to do for bell work was look at these two graphs and talk about the equation of them, right? Y equals mx plus b. Should be a nice little throwback to Algebra 1. For this one, yeah, they're throwing in bells. For this one, you can see the y-intercept's here at 1, right? And from there, it goes up to over 3, so that'd be y equals 2/3 x plus 1. And same with this other one. This one starts down at -3, and then, well, we can't follow the slope down this way, so we'll go the other way. So go 1, 2, 3, 4, and then over -1. So 4 over -1, that's just -4. So we got y equaling -4x, and then -3. So hopefully this is familiar, it rings a bell. There were a couple kids last year who were a little rusty on slope and y-intercept and all that stuff, so I just wanted to at least readdress it right here. But the other thing I ask is that, what does this slope mean? A lot of people can give me the equations, but then when I ask them what does that slope actually mean, they struggle. So first of all, obviously the slope is this part, right? Right in front of x, the slope always goes with x. Should be something you know already. But what it tells us is basically what's y doing every time we go over x. Like here, every time I go over 1x, y goes down by 4, right? Same here. Every time I go over an x, y goes down by 4. And this one kind of works the same way. Every time I go over x, I go up 2/3, right? That's 2/3, that's 4/3, and that's 6/3. 6/3 is 2. Hey, I went up 2. It works. It's just like that. So, when we're looking at data, and we're looking at data that's linear, which we talked about a lot before we left, you're going to use these linear equations to try and model them, to try and predict what's going to happen with future data points based on what we already know. So let me get this off here. Alright. So, I'm going to show you guys in calculators how to make these models. So, really it's the same as what we've been doing. So what you'll do, first you will get your calculator out. I'm going to zoom in, make sure everyone can see. A giant calculator. So what I did is I took our data between height and right foot length. And this is a data set that a lot of guys used in your activity that we did, where a lot of you got to pick which data set you used. A lot of you thought this would be strongly correlated, and those you did found out you were quite right. That correlation coefficient was very strong. So the height, and then, what is it, R, F, L. Alright, I'll enter these in slowly so that you can practice typing in if you want to get some practice with that. If you're good with typing this in, you just want to skip forward, you can. That's fine. If you already know how to do this, again, you can skip forward. That's not a big deal. That's the great thing about videoing these. Yeah, 63, 64, 60. Hopefully you guys can see those numbers. Let me try this. Oh, that's way better. Yeah, that should help. Yeah, 60, 64, 60, 72, 69, 62, 66, 62 again. I'll pause, let you catch up if you're following along. 67, 59, 68, and 62. So you can go through, make sure you have everything right. It should be 12 data points total. So if you don't end in cell 12, then you're making a mistake. And then the right foot lengths, 8.75, 9.25, 8.5, 10.5, again, 9, 10, and 9. And then we've got a 10.5, 7.75, 11, and 9.5. So if I want to go through one time, just make sure your numbers are right. Again, if that was too fast, you can always pause the video. Alright, that should be all good. Yeah, so just like before, you go into menu, go into your statistics, stat calculations, linear regression. Does not matter which one you use. I'm always going to use this one just because you guys are more familiar with mx plus b. A plus bx will just give you the y-intercept first and then the slope. But again, mathematically, absolutely no difference between where you put them. So we'll just use this one. Again, that's the one I usually use. Whoops. No. I picked the wrong one. Let's try this again. 4, 1, and then number 3. X list, of course, is going to be my height. I'm going to use that to predict right foot length. Again, make sure you know which one's your explanatory, which one's your response, folks. In this case, I guess you could go either way. But I'm just choosing height to predict right foot length. Alright, so we hit OK. And then, our equation's m times x plus b, right? And then it gives us right here, here's m and here's b. So you can see your m, your slope, is 0.227, approximately. I'm going to round that. And then negative 5.125 is your y-intercept. So the equation would just be this. You just get y. Now, the thing about regression equations, the actual y values are the data points, right? This equation isn't going to give you the actual data points, it gives you the predicted data points. And so we actually call it y hat. It's like p hat, it's like our sample proportions trying to predict the population proportion. Y hat helps us predict what the y's are going to be on our regression equation. So we have that, and then that equals mx, so it's 0.227, x plus b, which is negative, so we'll do minus 5.125. I'm just going to round that. So that's how you get from here to here. Whoops. Come on, there we go. So in case you didn't already know that, that's how you get your equation in the calculator. Use your m and your b, that's your slope, that's your y-intercept. So, once you're able to do that, what I was going to have you guys do is try it out here. Now, what we're going to do now with this equation is first, you're going to predict right foot length of someone with a height of 64 inches. Then you're going to do it with a height of 65 inches, and then you do it with a height of 66 inches. So what I'm going to encourage you guys to do is try it out. So pause this video for a moment. Try this out. So basically plugging in 64, 65, and 66. And then what you'll do, as the height increases by 1 inch, I want you to notice what happens with the y. So pause it. Try this. Okay. So hopefully you've already paused it and tried it. We'll see who actually did that. But what should happen is the following. So first it was 64, then it was 65, and then it was 66. So we're going to do y hat is 0.227, just plug in 64, minus 5.125. And then we'll do it for 65. And we'll do it for 66. So, you can just use a calculator. There's nothing wrong with that. No shame in that. Oops. Didn't get it to work. There we go. So, let's plug these bad boys in. I'm trying to see how I can, I have to zoom it out. So we can fit everything in there. That's a little better. We have 0.227 times 64 minus 5.125 6. So there's your 3 answers. Might be a little blurry, might be a little small. I'll write them down a little bigger. So you should have gotten 9.403, 9.63, and 9.857. So as our height goes up by 1 inch, what's happening to our right foot length? How much is that going up by? Well, what are we multiplying our inches by? 0.227, right? Well, let's see if that actually works. If I start with 403, and I add 0.227, oh, there it is. There's my 9.63. And if I do that plus 0.227, well, then I get the 9.857 that I got right here. So every time, what's happening? As I'm going up, 0.227. So that's what that slope tells us, folks. The slope tells us every time my x value goes up by 1, what's going to happen to my y value? And in this case, every time my x value, my height, goes up by 1 inch, my right foot length, we would predict that it'll go up, on average, about 0.227 inches. Right there. So every inch that the height goes up, we can predict, or we could say that on average, based on our model, that the right foot length will go up by 0.227. So that's what slope tells us. That's what the whole point of these equations are. That's how we interpret those. And it's important to be able to do that because you'll see that on the AP exam a lot. I mean, I'd be surprised if you didn't see slope at least once. In fact, the free response last year asked about that, and a lot of kids got killed. So let's not let that happen again this year. You'll probably see it on the multiple choice as well. Remember, on the mock exam, there's about 3 or 4 questions about scatter plots and bivariate data. And I would not be surprised if that made another appearance. So, if you have questions about that part, please ask. Again, that's why I have a Facebook group. You can comment. You can always email me. Hit me up on the Remind app, on text alerts, if you're stuck on that. But let's talk about the notes. Let's kind of summarize what we just did and how we're going to be able to use this. So, let's see. Come on. Ugh. My computer's on strike too. Come on. Stop this. Come on. There we go. So our question of the day. How can I use bivariate data to predict the future? Based on what I know, what can I say about a future data point? For example, if we didn't have anybody in the class who was 65 inches tall, which I don't think we did, we can still estimate what their right foot length will be if they joined our class. That's what this is for. We can anticipate or predict what will happen with future data points based on the ones we already have. So, the notes. So, what we're talking about is this line of best fit. There's a couple different ways to calculate lines of best fit. This is the way we're going to use. It's called the least squares regression line. And in the next video, I'm going to show you why we call it that and all that. So we'll get to that. But for now, just know it's called the least squares regression line. That's the type of line of best fit we use. There's others out there. There's one called the median line. There's some other ones that exist. But we're going to do this one. This is the one that AP Stat does. And really, in the real world, almost all statisticians use this one. And again, y hat is a plus bx or ax plus b. Now, of course, you can always use m in place of slope. Again, it doesn't matter what variables the slope and y-intercept are because they're just going to plug in numbers there anyway. So, different statisticians use different things. Again, don't get thrown off if it's written this way. Sometimes the y-intercept will be first. Don't be one of those people that's always, oh, it's the first number, so it's slope. Slope is one that goes with x, no matter where it is. Slope always goes with x. Again, you should have learned that in Algebra 1, but make sure you know it for now. Do not get docked or something like that. So what is just a linear function that estimates or predicts what y will be for a given x value. again, it's not exact. It's a prediction. It's not a guarantee. So if we get someone who's 65 inches tall, we said that their predicted height would be, let me cheat a little bit here, 9.63. Obviously, they're not guaranteed to have a right foot length of 9.63. They could be a little more, a little less. But we can predict that on average, 65-inch people should have a right foot length of about 9.63. It's an estimate. It's all about estimates. We're making a prediction of what's going to happen. So again, y hat. Gotta know that symbol, that y hat. That is what y is predicted to be at a given x value, not what y actually is. So there is a difference between y and y hat. Y is like the actual data point. What is the actual y value of that data point? Y hat is what does the regression line predict y is going to be. And once I show you guys the graphs, you'll see the difference. So like an actual data point is here, y hats are all along the line. So are you on the line or are you an actual data point? You're usually going to be a little bit different. And then I think the third video is going to talk about the difference between y and y hat and how they're related and how we compare them against one another. Slope, of course, again, like I said, the number that goes with x. Doesn't matter if it's first, doesn't matter if it's second. It's always a number that goes with x. Please do not make that mistake. Just messing that up. Slope is the number that goes with x, no matter what. Slope is the number that goes with x. So, the definition of slope. What is it for? What measures the amount that y is predicted to change every time x goes up by 1. Because, again, our previous equation, we had y hat was 0.227x, right? Minus 5.125. So 0.227, that's the same as 0.227 over 1, right? Change in y over change in x, second algebra 1. So y increases by 0.227. The foot length will predict to increase by 0.227 for every 1 inch increase in height. Change of y over change of x. Rise over run. Y is x. So what's y doing every time x goes up by 1? For each additional increase in x. Y-intercept. Now, the first thing about the y-intercept, first of all, it's also known as the constant. And in fact, that's what we're going to call it more often in this course. Y-intercept is the same as the constant. It's a good term to know, not just for this class, but any math class you might take. It's the number by itself. That's what that blank says. It's the number by itself. You guys should know that, right? Y-intercept is just the number by itself. The number that doesn't have x to it. Again, you guys learned that in Algebra 1. This is where x equals 0. And that's important because when we're interpreting it, if it asks you, hey, what does the y-intercept of this regression equation mean? What you'll say is, well, when x equals 0, here's what y would be predicted to be. And it won't always make sense. Like, for example, in our regression equation on heights versus foot lengths, our y-intercept was negative 5.125, right? So I would predict that a person with a height of 0 inches would have a right foot length of negative 5.125 inches. That makes sense, right? That's silly. There is no such thing as a person with 0 height, and there's certainly no such thing as a person with a negative 5 for a right foot length. But again, in theory, if we followed our equation all the way, that's what would happen. I also want to talk about extrapolation, because that is the issue I just talked about, right? Clearly, there's no such thing as a 0-inch tall person, and there's no such thing as a right foot length of negative 5 or so. The reason we had an issue is because we extrapolated. And extrapolation happens when we're trying to use a regression model to predict a value that is far outside the data you have. You know, our data, our x values only went from about high 50s to upper 60s, right? So do not use that equation to try and predict someone who's 30 inches tall. Don't use that equation to predict someone who's 80 inches tall. we don't know what the data does outside of the range that we have. So do not extrapolate. That is a mistake that people make. Do not make assumptions about data outside of the data range that you have. Or the data interval, I should say. I shouldn't use range, I should say interval. So our interval, if we look at the data earlier, where is it? Let me see. We went from 59 to 72. So extrapolating would be if we made inference about anyone below 59 or above 72. Now, if we went a little below or a little above, that's not a tragedy. We can do that. I won't kill you for that. Maybe not the best idea, but it's not the end of the world. But again, if you're doing someone like who's 80 or 90 inches, no. Or saying here, you're going way below 59, like 30 or 40 inches, little kid, not going to work. Don't use this model to do that. This model is not designed for that. This model is designed for this data set and data that is similar to it. So avoid extrapolating, please. And here's why. It's my little comic. Let's look at it for a second. So as you can see, the little graph here, if you can't read it, it says, yesterday she had no husbands. Today she has one husband. So we can see her rate of husbands per day is one husband per day. So if she follows this rate, she'll get a new husband every day. Now, of course, you can see how silly that is. Obviously, this woman's probably not marrying a new man every day. Hopefully not. But that's the thing about extrapolation. I mean, we're not going to conclude that she's gaining a husband per day just from this data set. Yeah, from yesterday to today, her husbands went up by one. But that's not going to happen beyond that. And that's what extrapolation is. That's why extrapolation is so dangerous. Outside of the data interval we have, the data might act very differently. So be careful about that. Just use common sense, guys. I mean, come on. Really, honestly, use common sense. So here's another example of extrapolation. If you predict that you'll get an 80 in AP Stat, what's your GPA? But if I predict that you'll get a 0 in AP Stat, what's your GPA? So for sake of time, I'm not going to do this, but the thing I was going to show you is that here, 80 in AP Stat, plug in 80 here, you'll get something reasonable, right? Well, if you plug 0 in here, if you predict a 0 in AP Stat, actually I'll do this one real quick. I'll subtract 1.8. So you have negative 1.8 equaling 18.7 GPA. I'll put this up here. And then divide away the 18.7. Honestly, it's not too hard. 7 cancels. So your GPA is negative 1.8 over 18.7. If you calculate that, although you should notice right away, negative divided by a positive, that's going to be negative. In fact, to be exact, it'll be negative, what? Let me see. Negative 0.096, approximately. Can you have a GPA of negative 0.096? No, of course not. It's not possible to have a negative GPA. Oh, that's why some of my Algebra 2 kids are trying. But yeah, that's the thing. We're trying to make a prediction about something we don't know. We're trying to make a prediction about a data set or a data point that is way outside our data range. The grades in AP Stat, none of them go below 30, right? All of them are at least in the 30s, go up to around the 90s. So anything outside of this is extrapolation. So anything like way above here or way below here, that's extrapolation, that's extrapolation. Don't do that. Don't extrapolate, because what happens, you'll get a situation that clearly is not right. If someone had a 0 in this class, I would predict they have a negative GPA, and obviously that's not right. No, not at all. So again, that's why we don't extrapolate. Please avoid doing that. Pretty please. I would really appreciate that. So, I have to sing more race real quick. Let's talk about examples. Come on. So, here is the first example. I'll give you all a data point, or a data set rather, and I let you guys enter that into your calculators. So, you're going to find your least squares regression line from your calculator, and then we'll go from there. So, again, just like before, we will, let me see, where's the thing? Alright, let me put my thing up. Let me see. Oop, nope, I don't want that. I want my spreadsheet, right? Okay. So we have the fat and the calories, right? So, I'm going to make fat my explanatory variable. So where's my F keys? We'll call it F. And let's call calories C, make it nice and easy. So, show you guys the table here. This should be, is that all the data points? They all quite fit. Zoom out a little bit. Yeah, the data should be 19, 31, 34, 35, 39, 39, and 43. So you get 19, 31, 34, 35, 39, 39, 43. For calories, I mean, you guys can see this in your notes. What am I saying? You can just type these in. You guys can see them. 590, 570, 640, 680, and 660. So we're going to make our regression line. Where is my thing? Okay, then number 3. So I'm using fat as my explanatory, calories as my response, and then there's my M and my B, right? So, y hat equals 11.0, it's 0555, somewhere around to 06 x, and then plus 210.954. So let's keep that at 0.95, just round that down. So 11.06x plus 210.95. Now you'll notice I have to define my variables. Just like in significance tests, you have to define your parameters. Guess what, folks? You have to do it here too. So y hat is the predicted number of calories. You have to say predicted number of calories. And x is the grams of fat. So now interpreting the slope. Remember, slope's 11.06, right? So the format you will use is that we can predict that y will increase, or if it's negative, decrease, by this many units, 11.06, for every 1 unit increase in x, right? Because 11.06 is just 11.06 over 1. You don't have to write this, I'm just showing you, change of y over change of x. So, the interpretation is, we can predict that the number of calories in a fast food burger will increase, because our slope's positive, for each increase 1 gram of fat. So again, we're going to predict that every time our grams of fat goes up by 1, the number of calories would go up by 11.06 on average. Next one is interpreting the y-intercept. So we can predict that when x is 0, there will be however many units of y. So x is our grams of fat, right? Might not hurt to label those. This is our explanatory, this is our response. So a fast food burger with 0 grams of fat, ew, would be predicted to have, so our y-intercept's 210.95, so 210.95 calories. So you can phrase it this way: we can predict that when there is 0 grams of fat, there will be 210.95 calories. I phrased it a little differently because that's the way that just came to my head. And again, as long as you communicate the right idea, you should be fine. But of course, watch my note as well. Actually, assuming that a burger with 0 grams of fat would have this many calories, that would be extrapolation, folks. So yeah, this is what the model says. I want you to understand this is what the model says, but I also want you to understand that our model didn't get data from any burgers with 0 calories or anywhere close to that. All the burgers here between 19 and 43. So if you're looking at a burger that's below that interval or way above that interval, this data might not work so well anymore. So again, this is what the model says, but this model might not know what it's talking about because it doesn't have any data points like this to go off of. So again, we're extrapolating there. So interpret it. I mean, this is what the model is saying, but just understand that the model might be lying. Or at least not lying so much as making an uninformed prediction. Alright, so that's basically all you need to know about these. Again, if you have questions, don't hesitate to ask. Let me see if my video is still working, see if I can get through example 2 or not. Let me see. No, it timed out on me. I'll give you guys the other examples in a further video, so stay tuned.